When we talk about rational functions, you see the word ratio, which should make you think fraction. And rational functions are functions where both the numerator and the denominator are polynomials. And as with any fraction, the denominator cannot be the zero polynomial. If I want to look at the domain, what I need to look at is what values would cause me trouble in the denominator. So the simplest way would be to set that equal to 0 to find the numbers that I need to exclude from my domain. So here's an example. Here's a function, and you'll notice that there's a polynomial in the denominator. So if I want to find the domain, I need to find out what numbers that I have to leave out of the denominator because it makes the denominator 0, which is undefined. So what we want to do is take this equation, which is the denominator, set it equal to 0, and solve. To solve this equation, I need to factor, set each factor equal to 0, and solve. I get x equals 3 or x equals negative 3. So if I get x equals 3 or x equals negative 3, it means those are the numbers that will make the denominator 0, so I have to exclude them from my domain. So my domain is a set of all real numbers except 3 and negative 3. In interval notation, we would write it like this. Okay, let's look at the graph of this rational function. I want you to see what happens as x gets really large in a positive sense. What's happening to my graph? You can tell here that the y values are getting very, very close to 3. So we say as x approaches positive infinity, f at x, which is our y value, approaches 3. All right, let's see what happens going the other way. As x gets very large in the negative sense, it looks like my graph again, my y values are a little bit less than 3, but they're getting very, very close to 3. So in that case, we would say as x approaches negative infinity, my graph of f at x, which are my y values, they also approach 3. So let's see what happens here in the middle. As my x's are approaching 2 from the left, my y values are getting very, very, very small, which means large in the negative sense. So I'm heading down here to negative infinity. So the way that I say that is as x approaches 2, and actually if I put a little minus sign there, that means as it approaches 2 from the left. So as x approaches 2 from the left, f at x is shooting off to negative infinity. And on the right side, as x approaches 2 from the right, look what happens here. My values for y are getting very, very large. So I would say as x approaches 2 from the right, f at x is approaching positive infinity. So you can look at the values of your y, which are your f at x values, your function values, as x either gets very large in the positive sense or very large in the negative sense. And then you can see that sometimes your graph will shoot off to positive infinity or negative infinity as x approaches another number on your graph. When your function shoots off to positive or negative infinity as x approaches a number from the left or the right, we call that a vertical asymptote. When your function approaches a number as x approaches positive or negative infinity, that is called a horizontal asymptote. So for our example, we have the line x equals 2 as a vertical asymptote and y equals 3 as a horizontal asymptote. If you look at this graph, I could draw a line at y equals 2, and my graph would hug it from the top over here and it starts to hug it from the bottom. This is the line y equals 2, and it's considered a horizontal asymptote. Likewise, there's a vertical asymptote right here at x equals -1. My graph hugs it either from the right or the left. So I have x equals -1 as my vertical asymptote. I want to look at this example just briefly because it does something that's a little strange. There are horizontal asymptotes. The horizontal asymptote, you'll see that as x gets large, it's starting to hug the x-axis here and here. So we do say that y equals 0 is the horizontal asymptote, but notice what happened. My graph actually crosses my horizontal asymptote, and sometimes that will happen around the origin. So just be aware of that. You'll notice on this problem that both sections of my graph are above the horizontal asymptote. That will happen sometimes, but they're both starting to hug this line as x goes to infinity and -infinity. And both graphs are hugging the line x equals 1 as they shoot off to positive infinity. So the vertical asymptote is x equals 1, the horizontal asymptote is y equals 0. Take a look at this graph. It looks a little bit strange. It does have a vertical asymptote because the graph does hug the line x equals 2, but there is no horizontal asymptote. Okay, now you may have noticed some connections between the graphs and their asymptotes and their equations. So we're going to look at a few examples, and I'm going to show you how, by looking at the equation, you can figure out what the asymptotes are. Let's start with the vertical asymptote. The vertical asymptote is always going to happen at whatever value makes your denominator 0. So if I take 4x minus 6 and set it equal to 0 and solve, 4x equals 6, so x equals 6/4 or 3/2. X equals 3/2, that vertical line is going to be your vertical asymptote. Now for horizontal asymptotes, we're going to take a look at the lead term in the numerator and the denominator. Because when x gets monstrously large, this plus 5 and minus 6 are going to be pretty inconsequential. But if I look at the two terms here, if the variables are the same to the same exponent, then what happens is I can cancel this x with this x, and I can simplify this to 1/2. So my horizontal asymptote is y equals 1/2. All you need to do is look at the first leading term of the numerator and the denominator and simplify that fraction. Okay, let's look at this one. The value that will make my denominator 0 is 2. So x equals 2 is my vertical asymptote. For my horizontal asymptote, I need to look at the leading term. I'm going to do the same thing I did with the last one. I'm going to put a box around my leading term. Now I don't have any x's that will cancel, so then what I have to do is say, well, what does that box look like as x gets monstrously large? Well, if I have 1 over a billion or 1 over a trillion, that's actually a very, very tiny number. It's almost 0. So in fact, what I say is y equals 0 is my horizontal asymptote, because this fraction, as x gets large, is going to get very, very small. For this problem, to find the vertical asymptote, I need to look at the denominator and say what will make that equal 0. And the answer is -1, so x equals -1 is my vertical asymptote. For my horizontal asymptote, I have to look at the leading term from the numerator and the denominator. And if I simplify, this x will cancel one of these, but I still have an x. So what happens as x gets large, this is x, it's going to get large. So it doesn't come to a certain value. This fraction as a whole is going to continue to get larger and larger and larger as x gets larger. So there is no horizontal asymptote. So anytime the variable on the numerator has a larger exponent than the variable in the denominator, you're not going to get a horizontal asymptote. All right, when you look at this denominator and I try and find my vertical asymptote, it's not really clear the way it's written. But if I can take that denominator and factor it, then I can easily tell that what makes this factor 0 is 3, and what makes this factor 0 is -2. So I have two vertical asymptotes, x equals 3 and x equals -2, because those are both values that will make my denominator 0. Now for the horizontal asymptote, I don't want to look at this format. I want to come back and look at this format. When I look at the lead term in my numerator and my denominator, if I simplify that, the x in the numerator will cancel one of the x's in the denominator, and I've just got x left. So when you look at y equals 2 over x, and you kind of look and see, well, what happens as x gets large? As x gets monstrously large, 2 over a monstrously large number, like 2 over a billion, is very close to 0. So this is y equals 0, because as x approaches infinity, this fraction is going to approach 0. So this one had two vertical asymptotes and one horizontal asymptote.